this is actually, it's been relabeled. This is Chapter 17, Part 3, and technically also Chapter 18, Part 1. We're going to be discussing carboxylic acid, aldehydes, and ketones, predominantly in greater detail. So let's go ahead and get started. Our learning objectives, our candidates should be able to describe the formation of carboxylic acids from alcohols, aldehydes, and nitriles. Nitriles are when you have an organic molecule that has cyanide attached to it, just as a reminder. And then the other learning objective is to describe the reactions of carboxylic acids in the formation of salts, alkyl esters, and alcohols. So this is all about carboxylic acids. And so let's first of all take a look at the bell work. Bell work says, which compounds when heated under reflux with an excess of hot acidified potassium dichromate, which is K2Cr2O7, potassium dichromate. And the 6 is because the oxidation number, the charge of chromium is +6. That's why the 6 is there. So which compounds give a product with a chiral center? So I am going to go ahead and write the products out. This is a primary alcohol. So the first product, primary alcohols, get oxidized to become carboxylic acids. So this would be my first product. And so the question is this a chiral center? In order for this to have a chiral center, you have to have a carbon which has 4 separate groups surrounding it. So I look at the carbon in the middle because that seems to be the one that has the most groups that are different coming out. So to the left I have CH2, CH3. On the top I have CH3. On the side to the right I have CO2H. And on the bottom I have H. All 4 groups are different from each other, so that is a chiral center. So let's take a look at the next one. For number 2, you can see that this is also a primary alcohol, so it should be converted to CO2H. Well, this carbon now has CO2H, CO2H on it. Those 2 groups are the same, so therefore that would not be chiral. And let's take a look at the last one. So well, actually, we don't even need to, because once we have demonstrated that answer 1 is correct, but answer 2 is wrong, then the answer has to be D. Alright, so reactions that form carboxylic acids. They're formed from the oxidation of what? So the answer is primary alcohols and aldehydes. They are both converted into carboxylic acids. You do need to be aware of this reaction right here. If I would like to turn a nitrile into a carboxylic acid, it requires hydrochloric acid and water in order for that to occur. And that'll change your CN into a COOH. So, do you think carboxylic acids are weak acids, or do you think they're strong acids? You can kind of see the answer down here. Because you see the double arrow, they don't break apart completely, meaning that you have a weak acid. And that actually means that there would be a K associated with it, an equilibrium constant, established by having your products over your reactants concentration. However, we are not going to do anything with equilibrium with acids and bases. However, that would be discussed in the A-level course. It would be called the Ka, and it would be the same exact process we did back in Chapter 8 in order to establish concentrations of either your acid base or your starting acid. The usual reactions of carboxylic acid. Usual means these are all predictable. Predictable from, believe it or not, pre-ACE chemistry, as long as you remember how ionic compounds work. And so although CH3COH is covalent, the CH3COO has a negative charge and the hydrogen has a positive charge. Sodium hydroxide, sodium has a positive charge and OH has a negative charge. So when you see negative, positive, positive, negative, this means that you have a double replacement reaction. So in the reaction with base to form salt and water, this is really just a double replacement reaction, nothing strange here. Just remember that the positive will go with the other negative, so it would be H that goes with OH, and you would end up with CH3 kuna, because this is the negative positive and then positive negative. Reaction number 2, notice this is a compound, this is an element, so this is actually going to be a single replacement reaction where sodium kicks out hydrogen because it's stronger. So you end up with kuna and you end up with hydrogen getting kicked out into hydrogen gas. And then finally, if you form, this is another number 3, carbonates. If you form H2CO3 as a product, you do have to recognize that that breaks up into water and carbon dioxide. So this reaction right here is CH3CO minus H plus K plus CO3 2 minus. And so the negative charge would go with the positively charged, so CH3 cook. And then you would end up with H plus with CO3 minus 2. That gives you H2CO3. H2CO3 always breaks down for a final product of water and carbon dioxide. So these are all predictable, either single replacement or double replacement reactions. All right, well, let's take a look at a Cambridge question. An organic compound T undergoes the following reactions. What could T be? So, let's take a look at what we have. This right here is a secondary alcohol. This right here is an aldehyde. This right here is a tertiary alcohol. And this right here is a ketone. And so, they tell you that whatever T is, it can first of all be oxidized by KMnO4. And so we know that 2 of these choices actually cannot be oxidized. Tertiary alcohols and ketones cannot be oxidized. And so the answer cannot be C or D. And that would be from the first statement. The second statement says T reacts with sodium to give hydrogen. So the question is, would alcohols or aldehydes be more likely to react with sodium? Which one is more likely to give you ONA? Because this aldehyde is a carbonyl group, it's not going to be able to do it. This hydrogen would be the one that would have the ability to get kicked off, so it would in fact be the secondary alcohol that can both be oxidized into a ketone and that can react with sodium to give hydrogen. Alright, so carboxylic acids can be reduced. We spent the last lesson talking about oxidation, but we also need to be aware of the opposite process called reduction. And so remember, with oxidation, you're adding oxygens. So all of your oxygen, so all of your oxidizing reagents are compounds that have a large amount of oxygens. Whereas with reduction is losing oxygens or adding hydrogens. And so what you're looking for in a reducing agent is a compound that has a large amount of hydrogens. LiAlH4 is an excellent reducing agent. There's two reducing agents you need to be aware of for organic chemistry, and they look extremely similar to each other. The two of them are LiAlH4, that'll do reduction, and the other one is NaBH4. Now the difference between the two is lithium aluminum hydride is stronger and sodium borohydride is weaker, meaning that if you have lithium aluminum hydride, it'll take a carboxylic acid all the way back to an alcohol. Whereas if you have sodium borohydride, it actually won't react with the carboxylic acid. It won't be strong enough to reduce it, but it can take aldehydes and ketones. The weaker agent can still take aldehydes and ketones and turn them back into alcohols. So you do need this information in your notes for some of the practice reactions that you will see. And so notice that you are going backwards. You're going from carboxylic acid to an alcohol, carboxylic acid to an alcohol. You're adding hydrogens back in and taking away an oxygen when you are reducing. Okay, so let's talk about the reduction of aldehydes and ketones. Aldehydes and ketones would also go back to their alcohol. So this is really the inverse process of oxidation. Aldehydes will go back to primary alcohols. Ketones will go back to secondary alcohols, which makes sense because if you have this, and reducing is adding hydrogens, you add a hydrogen here, you have to take away this bond, and you add a hydrogen here, and you go back to a secondary alcohol. This type of reaction is also called a nucleophilic addition, where you're adding H+. I did want to show you the mechanism here. You do not need to memorize this mechanism. It's not part of the objective, but it is good to know the mechanism just to have understanding. So I want to start actually with redrawing out BH4 and why does that have a negative charge. So if I have NaBH4, why does that end up with a negative charge? And so the idea is that boron has 1, 2, 3 valence electrons. If boron is to connect and satisfy all of its valence electrons, it would connect to 3 hydrogens because it only has 3 valence electrons. So the only way it can connect to another hydrogen, because it doesn't actually have another electron to connect to another hydrogen, is if an additional electron was added from, in this case, sodium. And so an additional electron is added, making this bond possible and making this whole entire polyatomic ion negative. So I do want to bring that up, that this boron is negatively charged. And because it is negatively charged, it would go, and the curly arrow would go to the carbocation, which is positively charged. And what would happen is the second bond from the double bond would become a pair of electrons on the oxygen. So this used to be the double bond. And then the another pair of electrons from the oxygen would grab a hydrogen, and this curly arrow would go over to give you OH minus, and you would end up with an alcohol. Protonation means adding H plus, adding a proton. And so once again, you don't need to memorize this mechanism, but it's nice to be able to trace the steps. Diagram shows the structure of compound Z. What is the product of the reaction between compound Z and an excess of NaBH4? So what we're looking for here are the reactive sites. NaBH4 does nothing with an alkene. The alkene is retained. So we know the answer has to either be A or D. What would react with an alkene? This would be addition reaction. So either water could be added, an acid could be added, but we could do KMNO4 for that type of oxidation. But NaBH4 actually does not react with that. It does react with aldehydes and ketones to bring them back to alcohols. So our answer should be A, because that makes the ketone an alcohol and it makes the aldehyde into an alcohol as well. All right, so how would you make ethanoic acid from ethane nitrile? This was that reaction. You have to go back a little bit in the video, or hopefully you took the notes. CH3, CN goes to CH3COOH with the reagents HCl plus H2O. And then it says, write a balanced equation using structural formula to show the formation of sodium methanoate. I'll skip that one. It's just a classic reaction. And it says, name and give the formula of the reducing agent used to convert carboxylic acids. That would be LiAlH4, which is lithium, aluminum, tetrahydride. And the condition is it has to be an acid. All right, so the second part of the lesson focuses in on aldehydes and ketones a little bit more. And so your learning objectives, candidates should be able to describe the formation of aldehydes and ketones using Cr2O7 2- and H+. We've actually already done that. Reduction of aldehydes and ketones using these two agents. Hey, guess what? We've already done that, which is why I put these two lessons together. And the reaction of aldehydes and ketones with HCN and NaCN. So this should be really the only topic that's new, except I'm also going to address how to keep an aldehyde an aldehyde. So first of all, let's take a quick look at the bellwork. Which alcohol has a chiral center and can be oxidized to a ketone? All right. The alcohol that has a chiral center and that can be oxidized to a ketone. Let's take a look at A first. Pentan 2-all is CH3, CHOH, CH2, CH2, CH3. First of all, is there a chiral carbon here? The answer is yes, there is a chiral carbon. Then, can it be oxidized to a ketone? Well, you would take these two hydrogens away, and you would end up with CH3, C, O, CH2, CH2, CH3. So actually, yes, you would make a ketone. So once you get the correct answer, you don't even have to solve the rest. Let's take a look at the second bell work. When CH2OH, CH, CO2H is warmed with concentrated sulfuric acid, a cyclic compound is formed. What is the skeletal formula of the cyclic compound? So in order to be able to do this, we need to understand what type of reaction is happening here. So I'm first going to redraw this molecule out a little bit. CH2, I'm going to put the OH, C, H, double bond, C, H, C, double bond, OH. So what you have is you have an alcohol and you have a carboxylic acid. When you have an alcohol, a carboxylic acid, and some acid, you are forming an ester. So notice how all of your structures here are rings. It's because when you form the ester here, you're going to close that ring. So let's see if we can trace the steps. The oxygen from the alcohol bond would go to the carbon with the double bond oxygen. There would be a carbon, a single bond, and then a carbon with a double bond. And there should be altogether 4 carbons in your ring. So I'm going to take real quick D out because there aren't 2 carbonyl groups in your structure, so there shouldn't be 2 carbonyl groups in your answer. I'm also going to take out as an option A, because A doesn't make sense. The single bond isn't on the oxygen. The single bond is after the second carbon from the oxygen. So after, this one has it after the first carbon, so that's no. This one has the double bond after the first second carbon, so the answer is C here. Alright, so naming aldehydes and ketones, that is going back to organic part 1. You need to know that aldehydes end with al, ketones end with ONE, and nitriles is how you end CN groups. So for example, if I have CH3, CH2, CN, I count the carbon in the nitrile, and I call this propane nitrile. So this right here, 1, 2, 3, 4, 5, 6. So that would be what? Hexanal. 1, 2, 3, 4, 5, 6, 7. So that would be heptane nitrile. And then draw the skeletal formula of methanol. Meth means 1 carbon, so methanol. Propanol means 3 carbons with an aldehyde. 1, 2, 3, and aldehydes always have to be on the end, so propanol. And then pentane 3-one 1, 2, 3, 4, 5. I just do the little dots to remind me of how many carbons I have. And on carbon 3 goes my ketone. And so how do I leave an aldehyde? That is the question. In order to leave an aldehyde, you're going to need to heat your mixture gently. So heat gently is a condition. And as soon as your aldehyde is produced, it actually has to be distilled off, meaning boiled off as soon as it forms into another container. The reaction mixture will turn green from the potassium dichromate, indicating the oxidation has taken place. And so the procedure to keep the oxidation at an aldehyde is the following. You're going to set up a distillation, and then you add alcohol to the flask. And then you drip the solution of dichromate into the flask so that you have always enough alcohol is a solvent. And so then you have to keep the temperature of the flask below the boiling point of the alcohol and above the boiling point of the aldehyde so that you're not boiling all the alcohol out. And so that aldehyde will distill into another container. The idea is the following. When you have your alcohol and you change it into an aldehyde, it is not automatically, but it's going to quickly turn into a carboxylic acid unless you can maintain the temperature in such a way where as soon as the aldehyde is being formed, the aldehyde would boil off. So it actually has to do, reason this works is because of the difference in boiling point for aldehyde versus alcohol. And so you have to keep the temperature at a high enough temperature to boil off the aldehyde, but to keep the alcohol in the mixture. And it turns out, because alcohol has hydrogen bonding, whereas aldehyde has dipole forces, just dipole forces, the temperature to boil an aldehyde would be less than the temperature to boil an alcohol. So as long as you keep the temperature above the boiling point of an aldehyde, but below the boiling point of an alcohol, as soon as you make the aldehyde, it'll get boiled off. So it has to do with the difference in the boiling points because of the intermolecular forces. And so that is something that you do need to know and you need to be aware of to answer paper 2 questions on how to keep an aldehyde. All right, so just review. Oxidation of secondary alcohol. This would produce a ketone. And let's take a look at a question. It says, compound X is treated with 2 reagents successfully, forming compound Z. You end up with a mild oxidizing agent. Doesn't matter, they're not specifying. It could be KMNO4, could be K2CR207, whatever. And then they tell you they're using NABH4 to reduce. So the question is, what would you produce as your answer after these 2 steps? Let's analyze each step one at a time. So, oxidizing. This is a ketone, so it will not be oxidized. This is an aldehyde, so it will be oxidized. So my product for Y would be the following. Now, that's my product for Y, because I oxidized my aldehyde. And so now I need to reduce. But because I'm reducing NABH4, I don't know if you remember I said a little while ago that NABH4 only reduces aldehydes. and ketones. Therefore, the carboxylic acid would be untouched when you go to Z. And your final answer should be CO2H, double bond here, and CHOH, CH3. And that answer choice is A. All right, that is the end for today. I will be shortly posting the Cambridge question assignment, the first part of the Cambridge question assignment. That will be due on Monday. Have a great rest of your weekend.